chapter 6.1, we will learn about shear and movement diagram. We use this question as an example. First, we will find the reactions at A and B. To find the reactions, we will first find the vertical forces, which is the total forces will be equal to 0. So we assume the reaction to be positive. Then we will get our first equation. Secondly, we will find the moment. We take the moment at A and we assume clockwise is positive equals to 0. Then we will get for the moment diagram, we use the area of the shear force diagram. The moment starts from 0 as the moment is 0. And then we use the area here, which is 411.22 times 0.35. We get 143.27 at this point. And then we add with this area. Then we add back this area, 0.3 times 175. Then we get our shear force at the moment.
6.2 graphical method for confronting shear and moment diagram. This is one of the examples for this submethod. First of all, we need to find the relation F F A1. First, we need to find the relation. So we get FCY equal to the flow of 2 times then we get FY equal to 0. So we find this part to part. So the formula for this part is So for the formula is get equal to 18.75 minus 5 for the moment is so we can start to draw the shear force diagram. Then we take this one. Then we use 5.75 minus 15, we get minus 9.25. Next, is then we need to draw moment method. First of all, we substitute 0 to this equation. So we get then we sub 5 to the equation. So we get 1 for this part, we substitute 10 into this equation. We get 0. So with a curve length to 0. This is moment.
We are talking about 6.4 fracture formula. So this is one of the example from this subject. So we are required to determine the maximum tensile and compressive bending stress. So the given moment is 4 kilo-inch per feet. So first, we are required to find the Y bar. So the formula is Y bar equal to summation of Y bar over A times area or Y bar total area. And then we take this line as the bottom line. So 0.25 and then area is 0.5 times 3. Is 4 plus 2 3 times 0.5 and then this one 5.5 and 0.5. So the total area 0.5 times 4 plus 3 times 0.5 plus 10 times 0.5. Okay, so calculate it, we will get the answer of this one 2. We will get the answer 3.4 inch. Okay, so now we are going to find the inertial moment. Inertial moment total I bar plus AD squared. That is 1/12 times its base 4 and then its height 0.5 cube. Then plus its area 4 times 0.5 and then d squared. So the neutral axis is located at around 3.4. So you minus this half of the base. That is 3.4 minus 0.25 squared. And then we plus this 2 1/12. Base is 0.5. Okay, height 3 inch plus its area 3 times 0.5. And then neutral axis 3.4 minus half plus this one 0.5 times 1.5. So is 3.4 minus 2 squared. Okay. And then last one 1/12 base 0.5 height is 10 and cube plus area 0.5 times 10 and this one 3.4 here So this is 3.4. So the y bar for this is 5 plus 0.5 plus 0.5, so it's equal to 5.5. So 5.5 minus 3.4 squared. So calculate, you will get the answer 91.73 inch to the power of 4. Okay, so when you get the I, you have N, then we apply the Fletcher formula. So applying Fletcher formula, maximum stress is equal to NC over I. So for the maximum tension, max. So given moment is 4 kilo-inch per feet. So 4 3, and then change the feet to inch. 1 feet is equal to 12 inch. And then C. So C is the, so for tension you have to find the maximum C. The total here is 10.5, and then neutral axis is here is 3.4. So 10 minus 3.4, you will get length of this. So this is the maximum tensile. So 10.5 minus 3.4. So I is 91.73. So you will get the answer 3,750.12 psi. Change it to kilo, 3.72 kilos square per inch. Now we are going to find the maximum compression. Max. Okay. So N also same. 4 times 10 to the power of 3 times 12. So compression, you just find the minimum one. So it's the 3.4. 3.4 okay, over I, then 91.73. You will get the answer 1779.07 per square inch. So change it to kilo, 1.78 kilo square per inch. Okay, so this is the answer for this question.
This is for 6.5 unsymmetric bending. This will be the diagram. Okay, our question is to determine the normal stress developed at each corner of the section and specify the orientation of the neutral axis. Okay, this will be the diagram. First, we need to find the internal moment components. Okay, internal moment component. Okay, first is for y-axis, that is my equals negative 4 over 5 12 kmn. Okay, negative 4 over 5 is we find from here 4 over 5 and times with the moment rate. So you will get negative 9.60 kilonewton meter. Okay, next we find for z-axis, moment for z-axis, that is 3 over 5 times 12 kilonewton meter equals 7.20 kilonewton meter. Okay, this will be our z-axis, and this is our y-axis, and this is for the x-axis. Okay, for the next, we need to find section properties. Okay, for the section properties, we need to find moment of inertia about y-axis and also z-axis. Okay, this will be the moment of inertia for y-axis equals 1 over 12 times 0.4 meter times 0.2 meter cube. Okay, the formula is dh cube over 12. And the answer is 0.2667 times 10 to the power of negative 3, and this will be meter form. Okay, then we move on to moment of inertia for z-axis. Okay, this for the bending stress. Our next step will be bending. To find bending stress right after section properties, that is moment of inertia. The formula will be the normal stress equals negative mzy over moment inertia at z-axis plus with moment at z over moment of inertia at y-axis. Okay, this will be the formula, and we need to substitute for the B, C, D, and okay, this for the B. Okay, and the answer for this will be 2.25 megapascal. Next step will be for point C equals negative 7.20 times 10 to the power of 3 Newton meter, 0.2 meter. Plus negative 9.64 10 to the power of 3 Newton meter times 0.1 meter over the inertia 2667, and the answer will be negative 4.95 megapascal. Okay, we have found for the B and C, that is D and E. Okay, for D equals negative 7.20 10 3 7.20 Okay, for this 1.067 and 0.2667, we have found out earlier before for this using this formula for this moment of inertia. So we just substitute here and plus 0.1 the inertia, and the answer for this will be negative 2.25 megapascal. Okay. Next, we will move on to stress at normal stress at point E. Will be equals to negative 7.20 and cube Newton meter, that negative 0.2 meter, that's taken from the diagram, divided by the moment of inertia meter plus with negative 9.6 and cube Newton meter times negative 0.1 meter divided by the inertia. The answer for this will be 4.95 megapascal. Okay, now we have found the normal stress at 4 points over here.
In this question, we need to determine the maximum moment applied to the bead. The bead is the composite bead. The below one is aluminium, the above one is brass. So first, the given is the allowable of aluminium, brass, aluminium, and this one is the elasticity of the aluminium and elasticity of the brass. Okay, since the elasticity of the brass is greater than the elasticity of the aluminium, so we find the N by using the elasticity of aluminium divided by elasticity of brass is 6kx/9. Then we get N. Then we put N inside here to find the width of the brass, because the width of the aluminium is reduced to an equivalent width of the brass. So we put it inside. So this is from here. Then the next step is find the centroid, is the normal axis from the below one to certain point. So we use the formula, this, then we get from here to here, this is centroid, this is the centroid. So is 0.005 here times the area plus equal to 0.049289. So we get a y bar. Next, use the y bar to find the moment inertia. So moment inertia is given by formula this one. So since it's the cube, so it's a rectangular. So the I bar is delta BH cube plus AB squared. So substitute the value inside. This is for the kilowatt is 0.1023, then the height 0.05, then the important is this one, D. The D is for since the normal axis we get the y bar is 0.049289, so it's almost here. 0.049289. So to get the D is the distance from the normal axis to the center of the cube. So it's here. It's a D1. So we use 0.049289 to minus 0.05. Then for this one, the center is for this one, the above D. So for the D is here 0.07. We need to get this distance, this is D2. So we use 0.07 minus 0.049289 to get the D2. D1, D2. So we get the initial moment and the unit is this one. So now we need to find the failure of the allowable bending stress according to the pressure formula. So this is the formula and we see our I. Then we assume the failure of the mass. So this is the given value, given stress. So it is over 6 equal to 10 C 0.09 minus 0.049289 over I. And get n equal to 10 is also equal to 6.1. Okay. C is the maximum radius for the normal axis. So for this one bars, you can see from here. We want to find C is here. C. So we need to use 0.09 minus 0.049289. Then we move to the aluminium. This 1, 2, 10 plus 10 to the power 6. 0.692 so n equal to 2.391 e of 10 we get both of the maximum moment for